Hello and welcome to the program Sula's Big Adventures with me, Sula. This episode is about astronomical seeing. I'm making this video at the request of one of the viewers, Christopher. In astronomy, when we talk about seeing, we're referring to how much celestial objects appear to twinkle or appear distorted due to turbulence, different temperature layers, or wind speeds in the Earth's atmosphere. Poor seeing will result in loss of detail and, in the worst case, an inability to focus on an object. Bad seeing is most apparent when you're viewing the moon and the planets. It makes them shimmer, much like when you look at something through a fire. The shimmering caused by poor seeing will make features on the planets and the moon appear blurry and indistinct, and the craters and other features on the moon will be difficult to discern when the Earth's atmosphere is turbulent. Deep sky objects are not as badly affected by bad seeing as objects within our solar system, since your ability to see deep sky objects is far more dependent on good transparency and dark skies than objects in the solar system, which depend almost exclusively on having good steady seeing. The exception to this general rule is when you're trying to split close double stars, where poor seeing can dramatically inhibit your telescope's ability to do so. Poor seeing can occur on nights when it may seem like the sky is excellent in all other respects. No clouds, no light pollution, no bothersome neighbor's light, and maybe even no moon. And that's because seeing is dictated by something not as easy to detect as the clouds or light pollution or dew, and that's the steadiness of the atmosphere. The less steady the atmosphere, the worse the seeing. The sources of bad seeing are 4 areas of atmospheric disturbance that can affect your view of the night sky. Number 1 is the air surrounding your telescope. The column of air within a telescope's tube generates atmospheric disturbance inside the tube as the tube tries to reach a temperature equilibrium with the air outside. This is why it's so important to allow your telescope to cool down to the ambient temperature before you start observing or photographing. Number 2 is the atmosphere from the ground to about 100 feet off the ground. Disturbances here are caused by the ground itself, or a hot pavement, or your driveway, or your house, or even your own body, releasing heat that they've absorbed during the day as they too start to reach thermal equilibrium with the cooling nighttime air. The convection currents generated within your telescope's optical tube and in the air nearby cause the stars to twinkle. Number 3 is the central troposphere, above your house to about 3,000 feet up. Turbulence here is caused by topography upwind of your observing site, including populated areas, hills, or other obstacles that disturb the airflow. And number 4 is above the troposphere, where we find the jet stream. The jet stream is fast-moving streams of air that will blur the finest detail in celestial objects if they coincide with the region of the sky you're observing. The reason why the jet stream and other disturbances in the airflow cause bad seeing has to do with properties of light. When light from a star or other celestial object passes through a medium, and in this case I'm referring to the Earth's atmosphere, that medium affects, refracts, or deflects the light. And what causes the stars to twinkle are rapid changes in the refractive index along the light path of the stars. So what is the refractive index? Well, when light passes through a medium, the speed of the propagation of light is reduced compared to its speed through a vacuum. And the ratio of this speed is the refractive index. In simple terms, it's a measure of the amount that light slowed down as it entered the Earth's atmosphere, and thus the refractive index is an indication of how much the light is deflected. Near the ground, atmospheric refraction can produce mirages, and refraction can raise, lower, stretch, or shorten images of distant objects. And turbulent air can make distant objects appear to twinkle or shimmer. But in this video, we're only concerned with atmospheric refraction of light from celestial bodies that pass through your telescope. Predicting good or bad seeing is the same as predicting the weather. It's unreliable. However, there are a couple of predictors. The passage of a cold front, replacing previously warm air with colder air, often causes areas of local convection and hence turbulent atmosphere. Cold front just moved through. Warning, warning, poor seeing coming. Also, there's a strong correlation between good seeing and low wind speeds. You can check seeing conditions on apps such as Clear Outside and Zasteria. Both apps give assessments of the seeing for your particular location and by the hour. You can also look at an animated jet stream map on the internet on netweather.tv. But remember that the data is often dead wrong, and the best thing to do is get outside and check yourself. And you can measure the seeing. A star should have an airy disk pattern produced by diffraction. Diffraction is the spreading of light waves as they pass through your telescope's aperture. Bad seeing causes that pattern to be broken up into speckles that will show up on long exposure images of a star as a blurred image of the seeing disk. The seeing can be measured scientifically by measuring in arc seconds the diameter of the seeing disk or filled-in disk of a star. Good seeing is 1 arc second. Clear, cold nights with no wind. Very good seeing is 0.4 arc seconds. That's high altitudes with stable air. Excellent seeing is smaller than 0.4 arc seconds, and this may only exist in your imagination. As amateur astronomers, we do not need to concern ourselves with scientific measurements of seeing. And thankfully, there are 2 other methods of measuring the seeing. The first is a 5-point scale devised by Eugene Antoniadi as follows. 1, without a quiver, perfect seeing. 2, slight quivering with moments of calm lasting several seconds. 3, moderate seeing with larger air tremors that blur the image. 4, poor seeing, constant, troublesome undulations of the image. 5, very bad seeing, not stable enough to allow even a rough sketch. The Astronomical League provides a practical guide to assess the seeing and the transparency from your observing site. And in fact, you must record it for each session if participating in one of the Astronomical League's observing programs. And here's how. Seeing, to determine the seeing, you need to know how stable is the sky. It's on a scale from excellent to poor. Excellent would be the brighter stars are not twinkling at all. Very good would be the stars are twinkling slightly, but the planets are not twinkling. Good would be the planets are twinkling slightly. Fair would be the brighter planets are obviously twinkling. And poor, the atmosphere is turbulent and all objects are twinkling to the point where observation is not practical. The Astronomical League also has a way to measure the transparency, or how clear the sky is. Transparency is a measure of what you can see in the nighttime sky in spite of dust, smoke, haze, humidity, or light pollution. An easy way to measure this is to use the magnitude of the faintest star you can see by looking straight up at the zenith. This seems difficult to me, to look straight up into the zenith to see the faintest star you can see, but an even simpler way is to use the Little Dipper, Ursa Minor, as your guide. Hopefully you can see the Little Dipper. The scale is 1 to 7, with 1 being terrible and 7 being fantastic. And here's the scale. 1, if you can see Polaris, you can't see Polaris, and I don't mean it's blocked by a tree. Number 2, you can only see Polaris. 3, you can see Polaris and the 2 stars at the end of the bowl of the Little Dipper, Kokab and Faircat. 4, you can see Polaris, Kokab, Faircat, and any of the stars in the handle of the Little Dipper. And 5, you can see 6 of the 7 stars of the Little Dipper. And if you can, please tell me where you live, because I'd like to come visit. 6, you can see all 7 stars in the Little Dipper, and you're not lying or exaggerating. 7, you can see all 7 stars and the stars near the Little Dipper that aren't part of the stick figure. And if you can do that, you're one lucky devil, and you're probably young or you live in the middle of the desert. Keep in mind that there are other factors at work here, and one is atmospheric extinction, how much the brightness of the star will be reduced by passing through the Earth's atmosphere. And this depends on the season, your latitude, and the transparency. So using the Little Dipper is just a simple but rough guide to quantifying transparency. But that last bit was about transparency, and I intend to cover transparency and other factors that affect what you can see through your telescope in a subsequent episode. So for now, let's get back to poor seeing. What can you do about it? Well, scientific telescopes use adaptive optics by using a deformed mirror to compensate for distortion caused by bad seeing. For the rest of us amateur astronomers using amateur telescopes, try only looking at deep sky objects and not the planets, the moon, or double stars, which are the most affected by bad seeing. Aside from that, if the seeing is so bad you can't even focus your telescope even on galaxies and nebulae, well then, it's time to put it away and get some sleep, or try another night. Or it doesn't have to be the end of your observing session. There are plenty of wonderful sights in the night sky that are not affected by bad seeing or atmospheric turbulence. You can just lie back and observe the constellations as they wheel across the sky. Watch a conjunction or a meteor shower, or just look for a random meteor or a bolide, a nova or a supernova, or just enjoy the dome of the sky above. The universe is vast and there is plenty to see in it, even when the seeing is bad. That's it for now. I'll see you soon. Dark skies forever. Sula, signing off.